Hello, everyone. Welcome back. Today, we're talking about what's called the central limit theorem and how we can use that, the basics of it, and then explain a little bit about how it's actually used in statistics. So our goals for today will be to understand the basic concepts of the central limit theorem, and also be able to use this central limit theorem to determine probabilities using a standard normal distribution. So this is a theorem, a mathematical statement. And what it says, let's just read this part. It says for simple random samples of the same size, n, where n is greater than 30, then the sampling distribution of the means x bar can be approximated by a normal distribution with a mean u and a standard deviation of sigma divided by the square root of n. Okay, so it's kind of, look over here to the right and explain what that's saying. It's kind of a lot of words. But the idea is, let's say you have some distribution. And it could be any distribution. And the great thing about this idea is it doesn't have to be a mean distribution. It doesn't have to be it doesn't have to be a bell-shaped curve. It could look like this. Okay, you have some distribution that looks like this, where these are your, x values, and this is your frequency over here. So the thing is kind of like a continuous distribution. All right. Now, what we're going to do is just sample values from this, take samples of size, I'm going to call it small n, greater than 30. Okay. And also, let's say this distribution, let's say it has a mean. Let's say it's mu, the mean is right there. It has some standard deviation. So here its mean is mu. And has some standard deviation sigma. Okay. Now, we're going to take samples of this of size 30, random samples. And also, I should say random, I'll say randomly. Include that. That's important. Okay. As long as they're larger than 30. And this, as we'll talk about, this isn't really a law of math. It's just some kind of something that's been found in practice to work. Okay. Then what happens is that from the central limit theorem, what happens is if we take samples of size random 30, this distribution then, let's imagine we take lots of these, many of these samples, say many such samples. Okay, so imagine we randomly take a sample of, size 30. So we get a bunch of data points here randomly, 30 values. Then we do that many, many times, maybe hundreds, thousands of times. So what happens then, we get a distribution then of the sample means. Okay. And the sample means we're going to call x bar. Okay, so we're going to take all these samples, size bigger than 30. We're going to find the mean of each one. And what happens then, we make a distribution of all those means, those individual values. We can make a distribution of those, and it turns out that that distribution, as long as your sample size is bigger than 30, will basically have a normal distribution. Let's try that again. Okay, where the mean of that distribution is mu. Okay, the same mean we had up here. Okay, exactly the same. Many of those be in the same place. And then the standard deviation of this is going to be the population standard deviation sigma of the original population divided by the square root of our sample size. Okay, once again, this is a normal distribution, a bell-shaped curve. Now, this is a really useful result because, once again, as long as we take these samples, large samples, size, maybe let's say with hundreds, thousands, and then take the means of each, take the average of each of those samples. Those averages all make up a distribution. And no matter what kind of distribution we started with, even something looks kind of strange like this, what turns out is that we end up with a normal distribution with a mean exactly in the same place. And this is really useful. This is really powerful, because what it means is now I can, by doing this, I can actually use standard normal distribution techniques to find probabilities, okay, as I have in previous videos. Okay, so let's read a few more things about this. The means of the original population can have any distribution, but the distribution of sample means X can be approximated by a normal distribution as long as N is greater than 30. Once again, that's not something it's more just some seen in practice, not something that's just wrong or right mathematically. There are some special cases of non-normal distributions where N equals 30 isn't large enough. Those are rare. Also, if the original population is already normally distributed, we can take any sample size we want, which is also really useful. We can also do a z-score. Just we've done z-scores in the past, where this time instead of X, we use X bar, the averages of one of those samples, minus mu, and then our standard deviation is now this new standard deviation of sigma divided by the square root of n. Okay, so I can say one more thing about that. Okay, so we can find, so now this allows us then, if we taking these samples of size that's bigger than 30, I can use standard normal distribution techniques to find probability. This is really useful in what's called inferential statistics, when you're trying to basically infer something or make a guess about a population mean that you don't know. Okay, like political polling, for example, they're trying to find maybe the proportion of people like this candidate or another candidate. That's something you can't know for certain, but it turns out if you can take a sample maybe of 100, 1,000 people or so, often you can get a pretty good idea of what that proportion is. Okay. Now I want to show you a few more things before we move on. So let's go right here. So this is a central limit theorem simulator. And what we're going to do is we're going to pick a distribution. If I pick, let's say, a uniform distribution, remember uniform means all your values are the same, exactly the same. So you just get a flat, you just basically get a rectangle. So this is the mean of that distribution, and this is its standard deviation. Now, what I'm going to do is now it says click this like samples from drawing the sampling distributions. What I'm doing is going to take a bunch of samples of size 2, and then the distribution of the averages of those samples looks like this. It's not normal, which we wouldn't expect it to be. That's not that many. But what happens as we increase the sample size and take, so what we're doing is this person taking samples of size 2, a bunch of those, and find the average of each. And that's what you see plotted here, those averages. It's not normal, but we increase our number, take samples of size n, samples of size 9, take the average. All those averages are plotted as a distribution. Also says number of samples here, 20,000, which is a lot. You can see as we increase our sample size, it gets closer and closer to a normal distribution. Okay, closer and closer to that bell-shaped curve. And also, if you notice, because our sigma, our standard deviation is being divided by the square root of n, being divided by a larger and larger number as we increase our sample sizes, then this standard deviation gets smaller, and so our normal distribution becomes more narrow, becomes more focused. And once again, each time you notice our mean, let's go back and take a look at each one of these. So we're saying, let's start here again at 2. Our mean is the same, approximately 200. Our standard deviation is large, but as I increase the sample size, it becomes more and more like a normal distribution, and also our standard deviation becomes smaller. So that's, both things are a good thing. As the standard deviation becomes smaller, it becomes better to, if you're trying to find the mean, which you don't know, it becomes a lot easier to approximate it using these samples. Now, if we go back to a new distribution, let's pick one that's skewed, okay? Obviously not a normal distribution, not a bell-shaped curve. Here our mean is about 297, almost 298, and there's our standard deviation. So one's going to take samples of size 2, take those averages, also definitely not normally distributed, okay? But our mean is approximately the same, and our standard deviation is smaller. So as you increase our sample size, we see this becomes more and more normally distributed, closer to a normal distribution. Our means is approximately the same as our original population, and our standard deviation gets smaller and smaller, which is what we want, okay? Until we get to a sample size here. So 2,500 samples of 100 so we're taking 2,500 samples of 2,500 samples. Each sample is 100 measurements. Take 100 random samples out of this and average each one of those, and we get this normal distribution, which is a much narrower, much smaller standard deviation before the original one, but also the standard, the mean is approximately in the same place. So once again, this is really powerful because the idea is if I have this distribution I'm starting with, maybe I don't know much about it, don't even know what the average is, but if I take large samples, larger and larger samples, then the true mean of the population by the central limit theorem is going to be approximates the actual mean of the actual distribution, the original distribution, and the larger sample I take, the closer and closer I actually get to that actual mean I don't know. So we'll see in the future how I can actually use techniques to actually then get what's called a margin of error, or kind of a prediction of how close you actually are to the actual mean, where the goal is to try to find this mean, which you don't know. So do that with a sample, and this is how you do that. So the power of the central limit theorem is basically tells you I can take a sample which is much smaller than the original population, and then use that sample to approximate, determine, get a good idea of where the actual mean is. Okay, so let's go back and take a look at some examples, see how this works. So let's start with this example number 1. Human body temperatures are assumed to be normally distributed with a mean of 98.2 degrees Fahrenheit with a standard deviation of 0.062 degrees Fahrenheit. Now, our first one is going to be a problem like you may have seen before in a previous video, just using standard normal distribution techniques. And once again, this is originally normally distributed. So what's the probability that a healthy individual has a body temperature that is less than 97 degrees Fahrenheit? So let's draw a picture of that, a basic picture of that, what we're talking about. Okay, so here's our normal distribution. Here's our mean of 98.2, right in the middle. Okay, now here's 97. Let's say it's right here. And so the question is, what's the probability that a healthy individual has a body temperature that's less than that? So in terms of the area under the curve, we're looking at this area right here. Okay, now we know that we can convert that to a z distribution. And so our z is going to be 97 and minus 98.2 divided by 0.62. And if we do that, and also approximate that to 1 decimal place, we'll see what we get. And that's approximately negative 1.94. Okay, so now we go to the z distribution. So here's our mean, and this z should be exactly the same place. This z is going to be negative 1.94. So we're finding the same area, the same curves. Now I'm going to use Excel. Okay, so the probability that x is less than 97 is the same. The probability is z is less than negative 1.94. And let's go to Excel. And so the way to do that in a normal distribution is first do equals and type in NORM. Now we go to this one that says normal.s.dist. That's a standard normal distribution. It says returns a standard normal distribution, has a mean of 0 and a standard deviation of 1. Double click on that, put in our value, which is negative 1.94. And then what says cumulative, we want that to be true. So it's true. Okay. And so what that says, the probability of that is about 0. Let's just do 2 decimal places, 0.03. Okay. Or about 3%. Okay. So what this says, if I pick one person, a randomly healthy person, has a body temperature of less than 97 degrees Fahrenheit, what's the probability that person has naturally? A healthy person, that's their normal body temperature, average body temperature is 97 degrees Fahrenheit. About 3% of the population, a little bit less than that, would expect to have that temperature. Now, Let's take a look at part two. Part two is going to be a bit different. Because if a sample of 20 people is taken, what's the probability that they have a mean body temperature is less than 97%? How does this question differ from the first? So hopefully if you see, this is a different question. First time, I'm just taking one person to find the probability that kind of as a general population, what percent, have, what probability is that, or basically what fraction of people we expect to have a normal body temperature of 97 degrees, and that's about 3% or less. But here, this is a different question I'm asking. The question is, take a sample of 20 people. So here my n, my sample size is 20, and that's a different question. Okay, now, since this appears to be a fairly rare event, remember, anything less than the probability of 0.5 is considered to be fairly rare. The probability the individual would have a body temperature less than 97. Then what's the probability that a sample of 20 people randomly taken would have an average body temperature of 20? Okay, that, as you expect, would be very rare. Okay, so here my x bar is going to be 97, but my mean, my mu is still going to be the same. So 98.2, but now my standard deviation is going to be different. It's going to be 0.62 divided by the square root of 20. So let's do that. So 0.62 divided by the square root of 20. And so that's going to be about, depending on how you round, it might be slightly different. That's going to be about 0.14, about a fourth. Okay, so the standard deviation is much smaller. So this, what we're thinking about, this is now a sampling distribution. Okay, original distribution, I draw it a bit smaller this time, is a sampling distribution. So it's going to be narrower than the original distribution. Okay, although our mean is going to be the same as the one from our first example, 98.2. Okay, and then so it turns out this is actually going to be all the same positions, going to be much farther, much smaller proportion. So this is here is 97.00 degrees Fahrenheit. Once again, this is a sampling distribution. Okay, but once again, we want to find that area in the same way. Now, as we'll see, this is going to be as much smaller probability. So the chance that if you take a random sample of 20 people and they would have their average body temperature be that low is going to be really small, as you would expect it to be. Same way of thinking about like height. The probability of seeing someone who's say 6'7" or taller in the U.S., a man, is not that unusual. It's unusual, but not extremely unusual. But if I said I took a random sample of 20 people, 20 men of the population, and the average height was 6'7", you should be suspicious of that, because that'd be really, really unlikely. And this is the same idea. So let's find our z-score. So our z is going to be this x bar, 97, minus 98.2, now divided by 0.14. So we're dividing it by a number that's about a fourth smaller. So expect it to be quite a bit. He's an absolute value, a larger z-score, an absolute value, though still negative. 97 minus 98.2. And that's going to be negative 1.2 divided by 0.14. Right. So that's going to be negative 8.57, 2 decimal places. So that's really far away. Okay. So then if we do our z distribution, our picture, I'm going to try to draw the same as much as I can. So it should be the same picture. Okay, here's 0. Here is negative 8.57, though in reality be way, way over here. I want to find the area to the left of that. And so once again, with Excel, I'll do the same calculation I did just a moment ago. So now the probability that my sample mean is less than 97 is the same, and my probability by z is less than negative 8.57. And that's going to be, let's go back over here. So this essentially the same thing I just did equals, so now Rm, okay, norm.s.dist, my z-score negative 8.57. 7. Once again, true because I want a cumulative distribution. And wow, so that's that's an exponent, basically 5 times 10, basically 5 times 10 to the negative 18th. That's essentially 0. Okay, that kind of makes sense because once again, we're talking about an individual with a really, a probability of finding an individual with a such a small, normal body temperature. And they're probably finding a randomly taken sample of 20 people that average would be really unlikely. Okay. So once again, think of this as like the probability of finding someone that one person in the population is higher than a man who's higher than 6'7". Now, finding that this is like the probability of a random sample of 20 people and finding the average of those 20 people 6'7", that'd be also incredibly unlikely. So if you got a result like this, you should be really suspicious of that. And that's part of what makes up statistical inference is the idea of, is this value that I got, does it make sense? Is it really from the population I think it's from? Okay. So now, why can normal distribution be used in question 2, though the sample size is less than 30? So we know our sample size in this case was equal to 20, which of course is less than 30. But the original population is normally distributed. So if we go back to our description of our central limit theorem, what it said is that if the original population is normally distributed, I can use any sample size I want. Okay. And actually, we go back to our simulator, we can see that. So let's see, where was that? Okay. Now let's actually do a new distribution. Let's do a normal distribution to begin with. But now if I take sample size of n, all these being less than 30, yeah, they're all basically normal. Okay. Even up to 9, even up to 25. So if your original distribution is normally distributed, I can take any sample size I want, even small ones, and get a normal distribution. Okay. So that's why. I can take any sample size work. So here, any sample size will work. Now, let's take a look at our next example. And actually, let me move this up a bit. Oops. Hang on. Let me change something. I need to undo what I just did. There we go. All right. Now let's move this back. Okay. Let's take a look at this example. All right. And this says quarters are now manufactured. Actually, I may actually skip this one. Let's do another one first. What about cans of Coke? I may do this one instead. It's probably a more interesting one. All right. Yeah, let's take a look at this one. This one said cans of Coke are filled, so the actual amounts have a mean of 12 ounces and a standard deviation of 0.11 ounces. Okay. Now, if you notice this one, there's nothing said about the distribution. We don't know if it's normal or not. It might be. We don't know. Okay. So the problem number 1 is a question about an individual can of Coke. On probably the single can of Coke has at least 12.19 ounces. So that's a lot more similar to the first one, the first problem we did. Okay, so our X is 12.19. Our mu is 12.00, and our standard deviation sigma is 0.11. So if we look at our distribution, now we don't know what the distribution looks like. In fact, I'll just draw it as something, like this. It may or may not be normal. Okay, but here is 12.00. And over here, the question is at least 12 12.19, so let's say that's right here, has at least that much. Okay. Now we're going to kind of assume for now it's normal to do this calculation of C. Okay. And so if we do a Z-score, and once again, I don't know, it might look like that. It might be normal, might not, but we can assume it's normal for this. We do a Z-score. So it's going to have Z is 12.19 minus 12 over 0.11. And let's do that. And that's going to be approximately 1.72 or 73 rather. Okay. So now then, if I use Excel, then if I look at my Z distribution, all right, you would have, depending on what the distribution likes, have the same shape. Okay, so I kind of made this a strange wiggly thing here, but you have the mean equals 0, and now in the same spot, this is 1.73. You want to find this area. Once again, I'm assuming it's normal just for the sake of doing this example. Then the probability that X is greater than or equal to at least 12.19 is the same as a probability that Z is greater than or equal to 1.73. And that's going to be the same as 1, since this is greater than 1 minus the probability that Z is less than 1.73. Remember, Excel and also tables give you the value to the left. So if we want to find this value here, we subtract 1, take 1, then minus the value to the right. Let's do that in Excel. So equals, always do an equals, 1 minus, and then normal distribution. So norm.s.dist, and then 1.73, and just always do true for this, TRUE. Okay. And so the probability of that, then as it says, is approximately 0. Let's go 2 decimal places, 0.4, about 4%. Okay. So once again, this is assuming a normal distribution. Okay, this would be true. Now, if you have a different kind of distribution, we don't know. So this saying this, given this value, we can give this value, but we don't necessarily know if we can trust it because we don't know anything about the original distribution. Okay, good chance it might be normal or kind of a bell-shaped curve, but we don't know. So this value, we can find the value, but we're assuming it is normal to do this. So it's hard to trust if we know for certain if that's right. But if we do a sample, we can be more confident in our values. Okay, so number 2, find the probability that 36 randomly selected cans of Coke have a mean of at least 12.19 ounces. Okay, so here our sample size is 36. And this time our X bar, so we're taking all these samples, we assume our sample, our mean, our X bar is 12.19, but our mu is still the same, which is 12. This time our standard deviation is going to be 0.11 divided by the square root of 36, which is, or square root of 36 is 6. So let's do that. 0.11 divided by 6 is, I'll go to 3 decimal places, so about 0.18. Sorry, 0.018 rather. 0.018, which is quite a bit smaller, 6 times smaller. So expect our Z-score to be 6 times further away. And so as we expect, this is going to be a really low probability. It's already a small probability, assuming a normal distribution. This is true. This is going to be really small, but we'll see that. Okay. Now, so this time, this is what's called our sampling distribution. Now this one will be normal. And also the sampling distribution for n equals 36. If we have a larger, I should point that out up here as well. If I do that. This is our sampling distribution for n equals 20. Let's go back and make that clear for that one. Because our sampling distributions will look slightly different for different n's. They'll be larger the n, the more narrow distribution will be. Now this will be a normal distribution. Let's say it looks like this. Okay. Although with a smaller sample size, it'd be wider. Larger sample size would be smaller. So right here is our same mean of 12. Okay. And way over here, this time is our 12.19. So this is going to be a really tiny area. We do the z again. This time it's going to be z. It's going to be our x bar, which is 12.19 minus 12. Our population mean, once again, is the same. The sampling distribution is the same population mean as the original one. Then our sigma is going to be 0.018. So let's do that. So wait. So that I got, they're very large in terms of z's, they're really large numbers. So that's approximately 10.56, which is way over here. All right. Now, if you look at our z distribution of the sampling distribution, this should look exactly the same. And let me try and do a better job of that. Okay, here's 0. And in the same spot over here is 10.56. I'm going to find that area. So it's going to work essentially the same way. It's the problem that x bar, our mean, is greater than 12.19 is the same as a probability greater than equal to that z is greater than equal to 10.56. And that's going to be equal to, in the same way, 1 minus the probability that z is less than 10.56. So let's do that over here on Excel again, just as we did. All right, so this time it's going to be equals 1 minus, then just start to type it in ORM. So norm.s.dist, and then 10.56, and then true. See, this is going to be really, yeah. In fact, even as it was so small, basically, to the accuracy of Excel, it gave us 0. This is also approximately 0. Okay, so basically the chances of that, so what that means then is if this is the true mean and standard deviation of Coke cans, of the volume and the amount of Coke inside a can of Coke, then finding the problem, if you take a sample of 36 randomly selected, there are randomly selected cans, and you got a mean of that, that's almost, chance of that is incredibly small, but it's almost 0. So if someone told you that happened, you should be really suspicious. So possibly they weren't actually random at all, because that would be so unlikely. That'd be the chance of that happening randomly is almost 0. So it does happen, you should be suspicious that it was actually a random process. Okay, let's actually go back to this one now. Then we'll do that one next. Let's go back to this one. Okay, so this says quarters are now manufactured. So they have a mean weight of 5.67 grams and standard deviation of 0.062 grams, and their weights are normally distributed. Okay. Vending machine is configured to accept only its quarters weigh between 5.55 and 5.79 grams. Okay. Now, if one randomly selected quarter is inserted into the vending machine, what's the probability that will be accepted? So what we're going to do then, this is based on the probability that our z, or x rather, our weight is between 5.55 and 5.79. Okay, so what we have then, and once again, we're assuming this is a normally distributed population. I already know it's normally distributed, so here's our mean of 5.67. And the question is, if we're between 5.55 and 5.79. So basically want to find this probability that we're in this area. So if we want our quarter to be accepted, what's the probability that one quarter will be accepted? It's a probability between those two. Okay. Now we need to find two z values here, two z scores. So we have z, I'll call it z1 is equal to 5.55 minus 5.67 over 0.062. And let's find that. And I got about 1.9 negative 1.94. Okay. Now let's call it Z2, the other end, the higher end is 5.79 minus 5.67. 0.062. If I do that, is basically the same value except positive. Okay, and that's not the way this problem is set up. That's not a coincidence. Okay, so now if I do, let's going to go to my z distribution. Should look exactly the same. This is, and we also know this is a normal distribution. Oops, try that again. Okay, here's 0. Here is the same place, so 1.94 and negative 1.94. So we're finding the area between those two values. Okay, and the way to do that in Excel is, so in terms of z, it's going to be the probability that you're between negative 1.94 and 1.94 is to take essentially the larger value. So the probability that z is less than 1.94 minus the probability that z is less than negative 1.94. So subtract the larger from smaller from the larger. Let's do that in Excel. And so once again, we do equals then the norm.s.dist, the larger value, 1.94 and true, minus then NORM, so type that in to find it right here, negative 1.94 and true. Okay, double check, make sure everything's right. So it's the positive larger value minus the smaller value. It equals, and that's about 95%. Okay, and hopefully that makes sense. I mean, about 95%, 0.95, two decimal places, because you want, a vending machine to accept, almost any, almost essentially all valid quarters. And so anything that's really unusual outside of, 5% chance of being too heavy or too light, then you might not want to accept. You want to accept most quarters. You want to accept 95% of quarters. Okay, now, if 4 quarters are randomly selected and inserted into the vending machine, what's the probability that the mean is between the same value? Okay, this time our same problem, except our n is equal to 4. Okay, this time we want to find the probability that x bar is between 5.55. Our sample mean is between that and 5.79. So based on what we've learned so far, we expect the probability of an acceptance to be even larger. Okay, even greater. And so once again, our original distribution, now this is going to be a sampling distribution, so it's going to be more narrow, though not a whole lot more narrow, because our sample size is still relatively small. And also the sample size is okay because we started with the normal distribution. So this is 5.79 over here. And then 5.55 over here. Okay, so we want to find this area in between those values. And then once again, this is our sampling distribution for n equals 4. Okay, that's important. A larger sample, a sampling distribution of a larger sample will be more narrow. Okay, it's going to do our Z1 and Z2. So it's going to be 5.5. Oops, I need to find my, my sigma now. The mean's going to be the same. The sigma is going to be 0.062 divided by the square root of 4 divided by 2, and that's going to be 0.031. Okay. And so actually, we can actually do this pretty simply. So actually, it's going to be half of each one of those. Okay, since we're dividing the points, as far as Z1 is going to be 5.55 minus 5.67 divided by 0.031. And since we're dividing by a number that's half, it's going to be twice what we had before. And so this is going to be negative 3.87. And then Z2 is going to be the positive value. That's a 5.79 minus 5.67 divided by 0.031. And that's going to be positive 3.87. And then if we find the probability, so the probability that we're between negative 3.87, same probability as this is the probability that Z is between this and positive 3.87. As you imagine, that's going to be this was the original one was 95% for 1. This is going to be even larger. Okay. And so once again, how we do that then is going to be the probability that z is less than the larger value, 3.87, minus the probability that z is less than the smaller value, negative 3.87. And let's come back over to Excel and do that. Is equal to, so find our norm.s.dis, so 3.87, and then true, then minus, then norm.s.dist again, the normal, standard normal distribution, negative 3.87. Once again, then type in true. Okay, double check, make sure everything is right. And then hit equals. As you can see, that's about 99. In fact, you have to go to, if you go out to about 5, was about 5 places. So let's just call it about 0.99989. And so basically, this is approximately 1 or 100%. Okay. So what this means, based on this information, okay, if quarters have this mean weight and this mean standard deviation, and they are from a normally distributed population, that means that if we take a sample, that a sample of 4 quarters, a chance that it's going to be in between those two values, these two weights, that sample, the weight, the average, back up. So we take a sample of 4 quarters, and we find the weight, or the average weight of those 4 quarters, that it's almost certain, almost 100% chance that it's going to be factored down to the thousandths level. So one out of just a few out of 1,000 samples, such samples, their average weights would not be in between these two. Okay, so what we learned today is understanding the simple limit theorem. I'm going to learn more in the future about how this is actually used to help us do inferential statistics. But the advantage of this central limit theorem is it allows us to start with a population we don't know much about. We don't know its shape and we don't know its mean. But it allows us then to take a sample of that population and then be able to say something, be able to approximate what that mean is, because as long as your sample size, if you're either starting with a normal distribution or if you're not, as long as your sample size is greater than 30, then the mean of this sampling distribution, which is made up of all the means of all the possible samples you could take of that size, then that sampling distribution has the same mean as the original population. And then also the larger sample we take, the closer we can actually get to that mean. That way we can actually then approximate what that true mean is. And that's really valuable for in any kind of polling or any kind of statistical analysis where you need to try and determine what the mean is, or to be able to say you're outside, your value is above the mean or below the mean, some statistical significant level. Thank you. Have a good day.